Readdy from the University of Kentucky and Princeton University, who will speak about my favorite subject, q-Combinatorics, a new view. Everybody who is in this room and promises to behave, meaning no cell phones and no electronic devices, is welcome to join us for dinner at 6:45. But please let me know immediately after the talk whether you can come. Thank you.
Thank you, Duran. So I'd like to thank Duran for the invitation. This is joint work with my graduate student, Yu at Tsai, my very talented graduate student. This is Jane. Okay, so as promised, let's start to count. So, according to Wikipedia, about 50,000 BC, we all began to count. And if you were a caveman or a cavewoman, and I don't know what to say, really, what were we? Who knows? And you were trying to count permutations in the symmetric group, what would you do? You would just count them, right?
Set stones.
What did you say?
Set stones down.
Too many stones, whatever. So let's say you're counting your permutations, the symmetric group, and the elements, and you count one for each, and lo and behold, you would get n factorial. Similarly, if you were counting subsets of the elements 1 through n, q-analogue k, count one for each, you would get the binomial coefficient and choose k, of course. Well, so this is counting, so now let's q-count. Ooh, this board is much nicer. Wow. Okay, so the idea of q-enumeration or q-counting is, this goes back to Euler in the 1700s. So Euler was actually interested in theta functions, but I'm not going to be talking about this. All right, so first thing I need is the q-analogue of the integer n. So quite often I'll just drop the subscript and just use brackets n. So this is just the sum of powers of q to the 0 plus q to the 1 up to q to the n minus 1. And here q is an indeterminate. Notice that if we take the limit as q goes to 1 of the q-analogue of the integer n, we get 1 n times, and we get right back to n.
But why limit? You can just plug it in.
Okay, I know you hate analysis, but it's fine, okay? We're not going to do any analysis today. I might do some topology, but I'm going to do it really fast. So, like, close your eyes or something.
Some sort of formula.
I only have 48 minutes. Come on, let's get going. Okay. God, what symbol?
Take a limit.
Q, arrow 1. Okay, calculus. Good. Okay, q-analogue. So now let's be very naive and say, okay, let me just say q-analogue of q-analogue of the binomial coefficient. We can define this way. Not clear it's a polynomial, but it is. So this is the q-binomial. So what you would like to have would be a nice combinatorial way to get at these q-analogues. So combinatorial interpretations. Okay, so these are due to McMahon. At least you can find it in McMahon's papers. It could be older, but I think it's McMahon. 1916, which says the following, is let's start keeping track of more structure with permutations. So let's keep track of the number of inversions in a permutation pi. So here, the permutation, we have this written in one-line notation. We're just going to look at elements that are out of order. So inversion number of pi is going to be the number of pairs, ij where I is less than j, but the entry pi I is greater than pi j. So we're just using one-line notation. And if we keep track of the inversion number, lo and behold, we get the q-analog of n factorial. Similarly, McMahon, again.
No, this is netto.
Oh, this is.
Netto, because
It
before.
goes back further. Oh,
50 years
good.
before McMahon.
Please give me.
No, with
references.
major index is McMahon.
That's right, with McMahon as major index. Okay, good. Give me references, please. And then, okay, so you'll probably correct me on this one too. So also appearing in McMahon's same papers, series of papers, is that what if we look now at words, or say pi. So let's look at the symmetric group acting on k copies of 1 and minus k copies of 0. And again, let's just take, so these are just strings of zeros and ones, length n, consisting of k ones and minus k zeros. Again, let's keep track of the inversion number, inversion number pi, and we actually get the q-analog of the binomial coefficient, the q-binomial coefficient. Do you have an earlier reference, I hope?
Yeah.
We'll see. Okay, so let's actually do an example. So we're going to do the q-analog of 4 choose 2, so I need to have sequences, length 4, 2 1s, 2 zeros. So let's right here. So 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 1, 0, 0, and we keep track of the inversion number. Okay, so here I have no inversions. Nothing's out of order. Everything's well placed. So I have 0 here. Here I have 1 inversion. The 1 and the 0 are out of order. Here I have 2 inversions. This 1 and 0 and this 1 and 0. Here I have 1, 2. Here I have 1, 2, 3. And finally here I have 1, 2, 3, 4. So it's 4. So we're going to take q to the inversion number, add these up. And can you see down this low? Is this okay? So then we get, I know these boards are impossible to do. Q to the 4th plus q to the 3rd plus 2q squared plus q plus 1. So this is q-analog of 4 choose 2. Okay? Okay, so next thing I want to talk about is the negative q-binomial. So this is new.
You can lift the.
No, we can't, because I have something under here.
Oh, okay.
And actually, the last time I was here 4 years ago, I haven't gained any muscles. It's like, you gotta WD-40, get it for your seminar. It's ridiculous. Okay, so what am I doing? Negative q. Negative q binomial. Okay, so this is due to Fu, Reiner, Stanton, and Thiem. I think it's Thiem. I don't know. I asked Dennis Stanton. He refused to tell me the correct pronunciation of his colleagues, so it's okay. So they had the following idea, very naive, seems sort of crazy, which is they say, okay, let's define the negative q binomial, which is let's replace q, negative q, and adjust the sign. All right, so going back to this example, good afternoon. You're slightly late, but that's all right. Q-analog of 4 choose 2 is, so it's the same polynomial, except it's worked out with the sign, so this is going to be leading positive coefficient. So q to the 4th minus q to the 3rd plus 2q squared plus minus q plus 1. If I can remember that. It's going to be q to the 4th minus q to the 3rd plus 2q squared minus q plus 1. Okay? So the result that's actually interesting, starts being very interesting, is that the following, again, this is their result, says that we can actually write this as, so remember, usual q binomial a combinatorial interpretation is looking at these strings and computing a version number. So what they did is they said, no, we can actually compute this for the native q-binomial in a subset of these strings. So I think I use pi. I want to keep my notation saying, oh, W. W and so this is the notation they use. Omega and A prime, and they have some weight function. And in particular, it looks like the following. Q to the, I think they used A. Yeah. So A of W, and then Q minus 1 to the P of W. So I haven't told you what these things are yet. Where this omega nk, I think the prime is some subset of these strings of zeros and ones. And then we have these two statistics. So there's some pairing operation. So P of W is going to count the number of 1, 0 pairs. I'll tell you what that is in a moment. And then A of W is going to be the usual inversion number minus the number of pairs. Yeah, inversion number minus pairs. So the whole point is that their degree stays the same. So let me say something about this pairing. I didn't want to spend too much about this. So let me actually. So the pairing is the following. So you look at one of these words, you count how many ones you have. If it's even, then you start pairing things as singleton. So going from left to right. So right now I just have the 0. Again, I look to the left, I just have two ones still. So I have a singleton. Here I still see 2 ones. Singleton. Oh, now I have an odd number, but I only have one element left, so it's 1. Same thing here, singleton, singleton. Oh wait, now I have odd number of ones, so I get a pair. So I have singleton, singleton. Oh, now odd number of ones, so I get a pair. Singleton. Oh, now I have odd number of ones. I can pair. Still have odd number of ones. Oh, by 1 element left. So I have to underline. So it's some pairing operation we have. Singleton, pair, singleton.
Okay, it's 1, 0 or 0, 1? Is it parentheses? In what sense is it pairs?
Oh, so there's a pair. The whole point is there is a pairing, a way to pair these. And then what they're going to say is this subset here is going to be the ones which do not have 0, 1 pairs.
Well, 0, 1 is...
So do not have...
So you don't mean consecutive 0, 1?
No, it's this pairing.
And this pairing.
This pairing.
So it's like parentheses, we have
You could put parentheses,
Yeah.
so underlining it.
Yeah.
So in that instance, the second permutation and the second from the bottom one are bad,
Yeah, bad.
but the other ones are good?
That's right, bad, bad. Is that it? I think that's it. Yeah. Okay, so rather than actually do the negative q analog of the binomial, q-binomial, let me actually tell you the corollary. And this is the thing that I love. This was the thing I was like, ooh, this is so beautiful. I love it. Wonderful.
Is it a coincidence here that all of them had odd number inversions? The ones which...
It's probably the way they came up with this.
Okay.
If you're the one who asked me a
Oh.
question, I think.
So it's not. It's not a coincidence.
I really don't know how they came up with this, but they did. Okay, so corollary to this. So Reiner again.
So what's the definition of 1, 0 pair?
Huh?
What's the definition of 1, 0 pair?
Oh, here. Here's a 1, 0
It's not,
pair. Here's a 1, 0 pair.
so 0 immediately followed by 1?
No.
No, it's you're actually
So-
counting how many ones you have.
So you have some algorithm for pairing them?
It's an algorithm, yeah. That's all you need to know. You shouldn't focus on this, because
Yeah.
otherwise you're not going to get to new stuff, right? And this is what you pay the big bucks for, the new stuff, not the old stuff, right?
No, I didn't understand it.
The big bucks,
Right?
right?
I've done those things.
We're never going to
Better
finish
to do it.
anything. We're not going to finish anything. I'll get half my abstract done. Okay, so then they say the q binomial can actually be written as the following. So again, summing over the subset, q to this A statistic, and then 1 plus q to this, whoops, P statistic. Okay, so let's actually go through that here. So, so this is what they call their weight. So q to the A statistic, 1 plus q to the P statistic. Okay, so remember, A statistic is going to be inversion numbers, but we're going to subtract off the number of these 1, 0 pairs. So here there's no 1, 0 pairs, inversion number is 0, so we have q to the 0, 1 plus q to 0, still have 1. Here, that gets thrown out. Here, we have 2 inversions. However, we have a 1, 0 pair. That's going to reduce the power of q down by 1. Q to the first times 1 plus q. Here, no 1, 0 pairs. We still have q squared. Here, we throw this one out. And then finally here, I have 4 inversions, but I have 1, 1, 0 pair. So this is going to be q to the third times 1 plus q. And if I haven't made any mistakes, when we sum this up, whatever, what do we get? We get 1 plus q times q to the third plus 1, plus q rather, plus q times q plus 1. And then we have plus q squared plus 1. This should be the same. Let's see. Q to the fourth, q to the third. I get a q squared from here, q squared from here. 1 times q is a q, and then I have a 1. So cowabunga, it's the same. Right. So then this leads you to ask the very natural question. So, goal.
So sorry to interrupt. Omega nk is a subset.
This is the whole point.
So what definition of omega nk again?
Excuse me?
Omega nk is a subset
It's
of
a
all the
subset.
words in k1s and m1s k
Exactly.
zeros.
Exactly.
So what's the definition of omega nk?
Prime.
Prime
So
is their notation. It is that you have this pairing operation, and you throw out all the sequences that have paired zeros and ones.
okay, whatever it is, okay.
Just maybe I should mention this. Dennis, I think, spoke about this at
Yeah.
your birthday conference, so
Oh.
clearly you were paying attention. You always complain about the rest of us. Now, tisk on you. Dr. Zalberg, sir, professor. Go.
A long time ago.
What?
It was a very 5 years ago.
You're older now. So give it a q-analogue. I'm
He
sorry.
was
this is hard.
probably going too fast, that's why.
Actually,
Don't be
it's
upset with
overhead.
anything.
It's overhead, seriously. So, give it a q-analogue.
You also go too fast, even though you choke.
Yeah. So, suppose you're given a q-analogue, and then the question is, find a subset T of S and statistics A and B, so that the q-analogue can be written as a subset of these elements, whatever the objects, q to the A statistic times 1 plus q to the B statistic. Okay, so this is the thing that I really said, wow, this is amazing. I wonder if we can do this for other classical q-analogues. So the work I'm going to be talking about today, whatever part I can get talking about today, is actually going to be talking about Stirling numbers of the first and second kind.
Oh, so you don't need to know this to understand the rest.
No, exactly. That's why I kept on saying, just forget about it.
Okay, I agree. Because to be honest, I don't quite understand it. And probably except for polynomials, which may be fast. Nobody has did this.
This is like the strangest
But it's
talk
okay,
I've
no,
ever
no. You could have said, understand
can't
that
have
is
two-
something similar.
And it's all on tape. That's the worst part about it. Okay. You're going to have like a million hits. It's going to be so scary. Okay, so let's look at q-Stirling numbers. So I'm going to start with q-Stirling numbers of the second kind. And just to say some sort of overview, hang on, how far yet, is, okay, so we're going to do the same sort of things for q-Stirling numbers of the second kind, start with those. And then we're going to actually see that there's more structure behind this. This is, there's actually a partially ordered set behind this, and then even you can start talking about homology computations. But I can't do too much of that because Stirling doesn't like topology. So, thank you. Yes, I know. Okay, so Stirling numbers. So let's start with Stirling numbers of the second kind. So this is usual counting, S and K. So this counts the number of set partitions of the elements 1 through n into K blocks. And I'm going to give an example. And this is going to be written in standard form. So set partition, it just means that I'm going to partition the elements 1 through n into a disjoint union. And of course the union is going to be the whole set. And then I'm going to order these blocks by their minimal element. So whatever the minimal element is of each block, the smallest one will be the first block, next smallest minimal element, second block, etc. So let's actually just look at S42. Some space. At elements 1 through 4 into 2 blocks. So I can have 1 as a singleton block, and then 2, 3, 4 is the other block. And again, notice the minimal element in this block is 1, the minimal element in this block is 2, so that's why I'm writing the order this way. And that's important. Then I can have, so this is block sizes 1 and 3. I can have block sizes 2 and 2. 1 with 2, 3, 4 is in a block. 1, 3, 2, 3 in a block, 2, 4 in a block, 1 with 4, 2, 3 in a block. So these are all the blocks that have size 2 and 2. Finally, I can have a 3 block and a 1 block. So I can have 1, 2, 3, 4 in its own block, 1, 2, 4, 3 in its own block, 1, 3, 4, 2 in its own block. So here we have 7. The Stirling number is 42 is 7. Okay? So the next thing I want to do is I want to encode these set partitions using something called RG words. So RG words. And this appears in work of Steve Milne. Another way, so RG stands for restricted growth words. It's also known as restricted growth words, restricted growth functions. Okay, so what does this say? So what I want to do is, given a set partition, what I want to do, so given a set partition, let's just apply, write, let's say F1 through N. So we're going to write a word length n, and where the ith entry, wi, is going to be j if the element wi occurs in the j block. So we're counting from left to right. So over here, our corresponding RG words. Okay, 1 is in the first block, 2 is in the second block, 3 is in the second block, 4 is in the second block. So it's 1, 2, 2, 2. Here we have 1 in the first block, 2 in the first block, 1, 1, 2, 2, 1, 2, 1, 2. So I'm sort of pointing to the numbers 1 through 4 in order. 1, 2, 2, 1. 1, 1, 1, 2. 1, 1, 2, 1. And RG word. Where this idea of restricted growth functions comes from, just so you know what it is these are functions where the requirement is that f at 1 is 1. In other words, this first element should always be 1. And we know that. Putting these in standard form, you know that whatever block the number 1 is, that's always going to be the first block. So of course, the first position is always going to be 1. And then the other thing, which might not be so clear, this is a small example, this standardization gives you, is that if you look at the, let mi be the max of the previous entry, so I'm going to write with this word w, so 1 is 1. You look at the max of the entries w1 to wi, and then you look at the next value, wi plus 1, this thing has to be, it could be in the elements 1 through mi, or it could be 1 more than that. So whatever it is, it's going to be bounded above by the max of the previous thing. So again, you don't see it here so much, but you know that once you're going to increase, that the most you can do from the previous guys is 1. It's the max. So that's why it's restricted growth. It's growing, but not too much. Okay, so we have that. Yes, so I should actually say q-Stirling numbers. So I should just give you the q-Stirling numbers. Oh, I shouldn't be writing it here. Sorry. So I'm just going to recurrence so you have it. Q-Stirling number of the second kind. S&K. This is going to be S, n minus 1, k minus 1, plus q-analogue of k times s n minus 1 k. And then, of course, there's boundary conditions. I'll just leave boundary conditions. I'll write it. SQ and n is 1. And this is the same as SQn1. Okay, so if you go back to traditional Stirling numbers of the second kind, just counting, forget about Q counting. So what do? If you have a subpartition of the elements 1 through n, you look at where n occurs, and if n is in its own block by itself, you throw it out, then you get a subpartition of the elements 1 through n minus 1 and k minus 1 blocks. Or if n was in one of the k blocks with at least one other element, and you want to put it back in after you threw it out, well, what's remaining is n minus 1 elements into k blocks, but then you have k blocks to choose to put it back in. So that's where this recurrence is coming from. Okay, so here we have q-Stirling numbers of the second kind. So let's actually give a statistic that actually generates these things. So this is a weight statistic. So let's actually call these restricted growth words corresponding to this q-Stirling number. Let's actually just call them script R and K, just to call it something. And let me define a weight on these. So for W and R and K, so let's let the weight of W, be the product of, so I have to tell you what the ith weight of W is. So here, that the first weight, the weight of the first letter, that's really what we're keeping track of, is going to be 1, and then the rest, so for the other entries, 2 up to n, what we're going to define, the ith weight of your word is going to be the following. So it's going to be q to whatever your position is, whatever's there, -1. So this is if